We have Gabriella here today, and you see Jasper's as well in a secret location, and we're going to try it a little bit different this time. So Gabriella sees you, so she knows that there's someone behind the screen. Jasper's the only one who can talk to Gabriella. If we want to talk to Gabriella, we have to say something on the Discord, and Jasper will relay it, or Gabriella will relay it. So that's how it's going to work. Is that okay? Any questions? Okay, cool. In that case, I'm going to now sit and give Jasper the secret signal so we can start.
Hey, okay. Hey, everyone. So welcome to ZuriHac, and today we're back with Gabriella. She is a Haskell programmer at Mercury and the author behind the amazing Haskell for All blog, which I'm sure we all read religiously. She's also written a large number of Haskell libraries and tools, including pipes and DAL that you may know, Turtle, and other things. She's also the author of a book called NixOS in Production, which is also very relevant for many of us. And today she's going to explain to us that monad transformers are actually a good thing. During the presentation, we'll have specific pauses for questions, so we'll probably be batching them up a little bit and then answering them. Yeah, Gabriella, please take it away.
Thank you. Thank you for giving me the opportunity to present here. I'm sorry I couldn't attend in person. There were some passport issues, so I have to present remotely today. With that said, I'll get on to my talk, which is titled "Monad Transformers Are Good, Actually." And the inspiration behind this talk is that I feel that, especially at conferences, monad transformers kind of have an undeserved bad reputation. And I kind of want to dispel that and show that they're actually quite good and actually my favorite effect system to use. And I hope to promote them and get more people to use them. Oops, 1 second. So the way I've structured this talk is in the first section of this talk, I'm going to motivate monad transformers and explain why you'd want to use them in your code. Because there actually are lots of professional Haskell programmers who have never used monad transformers, and you can get along just fine without them. So you might wonder, okay, what do I need them for if I haven't had to use them up until now? In the second part of this talk, there'll be a quick tutorial showing how to use them and the basics of how they work, and to build an intuition of what's happening under the hood. And then after that, I'm going to give a tour of some common transformers that you'll see in the wild to help you get familiarity with them. And then I'll talk about the two monad transformers packages, the transformers package and also the MTL package. And I'll compare and contrast the two packages. And then finally, at the end of this talk, I hope to dispel some common misconceptions about monad transformers. So the example I like to use to motivate transformers is an IO action that returns a maybe value, such as this readInt action. And so this action requires IO because it uses getLine. And the reason it returns maybe an integer is because we use the read maybe utility here, because it's going to parse a string from standard input, and that string might not necessarily be an int. So if it's not an int, we return a nothing. And this type signature is fine if I only need to call readInt once, but it starts to get a bit cumbersome if I need to call it 3 times and batch up the results. In other words, I want to define a read 3 ints function that is an IO action which returns maybe 3 ints. So if any of the ints fails to parse, I want the whole thing to return nothing. But if all 3 of them succeed, then I want to return all 3 ints. And the way I would do that is I would say, okay, first call readInt and bind that to this maybe int 0 variable, pattern match on it. If that's a nothing, then the whole thing returns nothing, we're done. Otherwise, if it's just, we keep going. And we need to repeat this process 3 times. And if all 3 repetitions complete, then we can return all 3 ints at the end of this computation. And this is kind of like really tedious, repetitive, lots of boilerplates. It's a very ugly code. I don't like writing code like this. And so what we're going to show later on is that if we use a monad transformer, and in this case, we're going to use the maybe monad transformer, then we can greatly simplify the code. So I'm just going to go quickly through this example. We'll break it down a little bit more later in this talk. But basically what I can do is if I wrap each of these readints in the maybe t data constructor, then I don't have to handle the maybe anymore. But I bind in this do block is the actual underlying int. So then I can just say, okay, bind int 0, bind int 1, bind int 2, and then return all three of them. And then at the end, I have to unwrap it using run maybe t. And the key thing I want to stress here is that the type of read three ints has not changed. So the use of the main monad transformer, at least for this specific function, is localized. It's an internal implementation detail of the read three ints function. But it's a very important implementation detail because it greatly simplifies the implementation. And here's another example of using maybe t. This one is less compelling, but I just want to include it for completeness. So suppose I want to keep calling readint until it succeeds. So if it returns a nothing, then just call it again. I can do that using this ensure int function, which will still return int. And I say call readint, and if it's a nothing, then just loop. Otherwise, we're done. And if I do it using maybe t, it's not that much shorter, but I want to highlight that if I wrap this readint utility in the maybe t data constructor, then that unlocks a new operator we can use, which is this alternative operator right here. So we can say, if readint fails, then fall back to looping again. We can think of this alternation operator kind of like a fallback operator. And there's a common pattern between those two examples. And actually, this is a very common pattern for monad transformers in general. We have some code of interest that we want to wrap. In this case, the readint utility. And then we wrap that in some monad transformer, such as the maybe t data constructor. And by virtue of wrapping it in this monad transformer, we unlock new functionality. In the first example, the new functionality we unlocked was simplified do notation. In the second example, the new functionality we unlocked was the alternative operator. And then when we're done using that new functionality, then we just unwrap the monad transformer to get back our original type. And the third step is the key bit. We want this new functionality. That's why we're using monad transformers in the first place. So here's a slightly more complex example. And again, I'm going to kind of gloss over things right now. I'm just trying to focus on the high-level motivation. So this is a very simplified way to implement a parser in Haskell. If you've never seen this type before, the idea is that if I want to parse a value of type A, one way I can model that is as a function, where the function takes an input string, which is what we want to parse, the string we want to parse the value from. And then there can be multiple possible parses, so I return a list of all interpretations. And then each interpretation has the value that we can parse from that string, as well as the remainder of the string that we have not yet parsed. And the reason we keep this remainder is so that we can chain parsers end to end and keep going. And so we might define a utility for parsing a single character called char. And then once I have that parser, I can create derived utilities like string. So if I want to parse each character of a string in succession, I can just say mapm. And then that'll just call the char parser on each character in a string, which is a list of characters. And the code I'd like to be able to write with this parser is something like this do block right here. I'd like to be able to say, okay, parse the string I like, and then after that, parse either the string cats or the string dogs. But this code, as it is, would not work unless I also provide a monad instance for our parser type. So that's because I need that monad instance so I can use do notation like here. And I'd also need an alternative instance for my parser too. So I can use this alternative operator here. And if I were to implement those by hand, this is what it would look like. I don't expect you to understand this code. I'm just showing you the size of the code involved here, right? So this is some tricky code, especially if you've never done it before, but this is how you would do it. But if we make use of monad transformers, we can actually greatly simplify this code right here. Instead, I can actually replace all these lines of code with this code right here. So if I enable Haskell's deriving via language extension, then I can just say, for this parser type, I want to derive functor, applicative, monad, and alternative. And the way I do so is by noting that this type for the parser is equivalent to a certain monad transformer stack. It specifically is the state monad transformer layered on top of the list. And again, I'm not going to explain that right now, but the point is that by noting that equivalence, then we can borrow the functor, applicative, monad, and alternative instances from that monad transformer stack. And we can reuse them for parser. So we save ourselves a ton of code just by recognizing that equivalence. Oops. So again, this is the same pattern as before. We take some code of interest, like our parser type, and we temporarily convert it to some other monad transformer, in this case, state T. And by virtue of that conversion, we can unlock new functionality, like these instances. And then when we're done, we just unwrap it to get the underlying type. And the driving via language extension conceptually takes care of that wrapping and unwrapping for us. All right, I'm going to quickly pause to check if there are any questions. Let me see. The question is, so the first question is, why not use compose IO maybe? And correct me if I'm wrong, but I believe there is not a monad instance for compose IO maybe. I could be wrong. But generally the thing is that like monads don't compose in the sense that like if you use data.functor.compose to compose two monads, then that does not necessarily have a monad instance. And we want that monad instance so that we can call like, read 3 int 3 times. Like otherwise it just wouldn't work. I guess in that example it would work because you're only really using applicative operations. But like for more complicated examples, you want the monad instance typically. All right, I think that's it for questions. I'll go back to presenting. 1 second. All right, so now I'm going to give a quick tutorial how to use monad transformers. So let's revisit our maybe T example and try to better understand why this example works. So if you look at the maybe T data type definition, it is a new type. So throughout this talk, I'm going to try to be careful about distinguishing between type constructors and data constructors. So the maybe T on the left-hand side of this is the maybe T type constructor. And the maybe T on the right-hand side of this equal sign is the maybe T data constructor. So the maybe T type constructor takes 2 arguments. The first argument is an M, which is the base monad. So it's some monad like IO that we want to extend with a new functionality. We want to transform it or upgrade it in some way. And for the case of the maybe monad transformer, the thing we want to do is we want to upgrade it with the ability to handle maybes transparently for us, so that we don't have to like explicitly pattern match on those maybes all the time. And under the hood, it's literally just like our underlying base monad wrapping some return value of type maybe A. And so by virtue of this data type definition, then that gives us 2 functions. So the first is the data constructor maybe T, which takes an action in the base monad that returns maybe A and upgrades it to a maybe T, which just returns an ordinary A, no maybe involved. At least the maybe is hidden. And then we have, of course, the unwrapping function, which is run maybe T, which does the exact opposite. And so M can be any type constructor that implements monad, like IO, for example. So if we replace all occurrences of M with IO, then basically it lets us wrap and unwrap values of type IO maybe int, such as our readInt function. So we take our readInt function, we wrap it in a maybe T, then now the type is maybe T IO int. And now this thing conceptually returns an int instead of a maybe int. So let's go back to the original example. I added lots of type annotations to try to better explain what's going on. So each of these readints wrapped in a maybe T has the type maybe t io int. And so when we bind their value, what we're binding is an int. So that's the type of int 0. It's just a plain int, no maybe involved. And then, so the type of the whole do block is maybe t io and then a triple of 3 ints. And then if we pass that as an argument to run maybe t, then that gives us back our maybe t free type, which is this type right here. But this example only works if maybe t has a monad instance, because otherwise we don't have a way to just chain these using do notation. So how does that monad instance work? So here's the monad instance. It's not that complicated, and I'm not really going to like step through it other than to note that this monad instance, especially the implementation of bind, looks awfully similar to the implementation of our read 3ins function. So if we look at bind, we say, okay, we take our first action m, and then we run it. We get a maybe value. We pattern match on that maybe value, and if it's nothing, we return nothing. And if it's a just, then we keep going, which is the exact same thing that our read 3ins function was doing, right? We for each action, we ran it, pattern match on the maybe. If it's nothing, we stop. Otherwise, we keep going. So conceptually, this bind implementation for our maybe t data type is the same thing as what we were writing by hand. It's just automating a pattern that we would have done otherwise. And so this is the next point I want to stress here, which is that monad transformers are what I would call natural. In other words, monad transformers arise from pre-existing code patterns that are found in the wild. They're not contrived things that we just invented for the sake of being architecture astronauts. All they're doing is just really factoring out code that we would have otherwise just written manually. And typically they're factoring out into the various instances, like the bind implementation, for example. And I want to contrast this with other effect systems, which have more alien implementations. So in the sense that these effect systems, if you look under the hood, how they're implemented, the actual code that they translate to is very different from the code you would have written by hand. And there can sometimes be good reasons for that. But monad transformers are just kind of they're the ones that are just kind of the natural evolution of code you would have just normally written. Sorry, give me a second. My alarm is going off. I'll be right back. Hold on.
Sorry for that. We'll resume in just a second.
Okay, so one thing that all monad transformers share in common is that they all implement the monad trans type class. And so this is the implementation of the type class. Again, don't dig into too much detail. The key thing is this is type signature of this lift function, which basically takes some action in the base monad, so a value of type, a value of type MA, and then lifts it to be an action in the transformed monad. So in this case, maybe TIOA. So we can take it, so in this case, I can take a value of type IOA and then convert it into a value of type maybe TIOA. Now, it might not necessarily be obvious why we want to have this function. So I'll try to show an example motivating why we want to have this class in the first place. So suppose I want to print the value of int 0 at this point in the computation where the comment is right here. The naive way to do that would just be to try, okay, what happens if I just put print 0 there? Does that work? No. And the reason that doesn't work is because there's a type mismatch. Every action in a do block needs to have the same monad, but this monad is IO, whereas the monad for all these other actions is maybe TIO. So the interpreter will reject it. All right, so the next most naive thing we might try to do is we might try to wrap that in the maybe T data constructor. But that doesn't work either because the maybe T data constructor has to wrap a value that has the shape IO maybe something. But that's not the type of print, right? It just returns IO unit in this case. So the last thing we can do to fix the type is use fmap just. And what that will do is it turns our print statement into one that returns a maybe value. And then once I have that, if I wrap it in the maybe T constructor, it has the right type to print something. And that is exactly what lift does for maybe T. That is how it's implemented. So to lift a value, you fmap just, and then wrap in the baby t data constructor. And then, so that means I can just have used lift here. And this is kind of why we want to use lift in the first place, is that it gives us a very convenient way to embed actions from the base monad in our surrounding transformed monad without having to do this complicated, maybe t fmap just stuff. And it works for every monad transformer. So that's another reason we want to have it. It's just a uniform interface for doing this. And all monad transformers support lift without exception. And the reason it's called lift is conceptually you're lifting the simpler monad into the more complex monad. And truthfully, like a lot of Haskell functions could have been called lift. Like as an example, you could argue that maybe the fmap function could be called lift too through a certain lens. But for whatever reason, this was the first function that people called lift, and the name stuck ever since. And so to recap, this is the way that all of our monad transformers are going to work. They take some base monad, M, and they extend it with a new feature, like ignoring maybes in this case. And then they provide a monad instance so that do notation still works. And they also add a monad trans instance so that lift continues to work. All right, I'm going to pause here and see if there are any questions in the chat. 1 second.
I don't think there's any.
Yeah, there's none.
It's
okay.
just too clear.
Yeah. Oops. All right, so far we've only talked about one monad transformer, or two, so maybe T and a little bit about state T. There's actually a whole menagerie of monad transformers. And the reason there are so many, but there are a few ones that we consider sort of like the standard monad transformers. And they're standard because each of these standard ones does one thing and does it well. And the idea is that if we want to do something more complicated, we will chain together these standard transformers to get the desired functionality. Oops. They each add, so each of these standard monad transformers adds some new feature to the underlying base monad. And you can keep stacking them as necessary. So let's start with the simplest monad transformer of them all, which is the identity T monad transformer. So this doesn't extend the base monad with any new features. It's literally a wrapper around the base monad. So the only thing you can really do with identity T is just lift actions from the base monad, and it just gets in the way. It's mainly there for theoretical completeness, and I guess there's some contrived scenarios where it would be useful. But like in practice, you're probably not going to use this monad transformer. I'm just thinking, including it for completeness, because it's the simplest one. So yeah, in this example, we just lift IO actions into identity T IO, and then we're done. Our first useful monad transformer is the reader T monad transformer. So this basically is a transformer that wraps monads that take a function argument. And it's typically used to thread a read-only configuration through your program. In fact, it comes with a useful utility called ask, which will take, and so the read-only configuration is this type parameter R here. And so that's how you know what you can ask for at any point in the computation. And if you use ask, its return value is the same type as that configuration. So here's the type of the configuration, here's the type of, and it returns that configuration. And so here's an example using the ask utility. So we say, okay, in this case, our read-only configuration is just a simple int. I'm going to ask for it. And so this end that we bind right here is going to be an int. And then I'm just going to print it using lift. And you might wonder, okay, so where does this end come from? And the answer is that it comes from here. Because when we unwrap our reader T action using run reader T, what we're left with is a function that will expect our read-only configuration, which is an int in this case. So this right here is that function. And so I'm going to pass 2 to that function. And then that 2 will get threaded to every place where ask is called. And so that 2 will get threaded to here, and then it'll get printed here. And the reader T takes care of that threading. That's basically what the bind instance for reader T is doing. It's just taking care to keep around that read-only configuration as you step through the various actions in the sequence. So our next monad transformer is going to be writer T, or the writer monad transformer. this is commonly used for outputting some sort of write-only value, which has to be a monoid. So in this case, it's a wrapper around some action of type M, which still returns a value of type A, but it also includes another output of type W, which is like our write-only output for our computation. And the way we stuff things into this write-only output is using this tell utility. So whenever in this W type parameter says what is stored in that output. So anytime we pass some value to tell, we will just add it or append it to the output. And then when we're done, we'll get them at the very end when we call run writer t. So here's an example of a computation where our output is going to, or our out-of-band output is going to be a list of ints. So anywhere within my computation, I can just call tell with a list of ints, and it'll stuff it into that output. So I can say tell the list 2 and 3, and then print the number 1 just for the hell of it, and then tell the number 5, a list with a singleton list with 1 5 in it. And so if I call run writer t, then, well, this unit will get bound to this type parameter a, which is unit here. But then all of these list of numbers will get bound to this w here, which is this numbers here in the computation. And so if I print numbers, it's going to print 2, 3, and 5. So this all got preserved. And so if you want a mix of both reading and writing values, that's what the state monad transformer is for. So this here is its model. So state in Haskell's model is a function. So our state type parameter is going to be s. In our function the input to the function is a starting state of type s, and the output is our return value along with an ending state of type s. And it comes with 2 utilities, a put function for overriding the state and a get function for reading in the current value of the state. And here's an example of using those 2 functions. So if our state is an integer, I can use get to read in that integer, and then I can print it. So that'll print 2 in this case, because our starting state here is 2. And then I'm going to add 1 to n, and then override the current state with that value. So the final state is going to be 3. So when I call run state t, then this value will be 3. And the final standard transformer I'm going to cover in this talk is except t. This is often used for throwing and catching errors. And you can think of it as kind of like it's spiritually very similar to the maybe t monad transformer we covered before. The only difference is that instead of returning a maybe, it returns an either. So they both short circuit. So like the maybe t short circuits when it returns a nothing, and except t short circuits when it returns an either. The difference is that with except t, like the either can actually hold a useful value in the left, unlike maybe t, which is just like a tacit nothing. So except t comes with 2 useful utilities called throw e and catch e. So throw e basically aborts the current computation and then returns a left value. So you just say, here's the value I want to store on the left, and we're done. We don't keep going. Unless you were to surround that with a catch block. So if you catch an error, you can handle it using catch e. And then you can keep going if you need to. So in this example, we're just going to throw without catching. So I'm going to say lift print 1, and then throw some string so our exception type here is string. So I can throw any value of that type. So I'm going to throw a string here, which means that after that throw, all the code after that is dead code. So this lift print 2 is not reachable. It'll never get run. And so if I run this example, it'll output 1. And then this e right here is going to be the value left. Oops. And so one thing that you should know is that a lot of these monad transformers have simpler analogous monads that are not transformers. So for example, the state monad transformer, the simpler version of that is just the state monad, which is not transforming any monad. It's just a monad. And you can see that they have very similar types, right? So here's the type of the state monad transformer. Here's the type of the state monad, right? It's basically the same, except we've just deleted the m from the data type definition. And indeed, their monad instances are also very similar too. But in practice, what we don't define them as two separate types and two separate monad instances. The way it's actually done in the monad transformer packages is that the simpler monad, like state, is defined as a special case of the more complicated monad. So what they'll do is they'll actually say the state monad is the same thing as the state monad transformer, except the base monad is the identity monad. And the identity monad is basically the do nothing monad, right? Like if you look at its definition, it just wraps the value and it's a new type. And so lots of monads are just special cases of a transformer. So the reader monad is a special case of reader T with the identity-based monad. Writer is a special case of writer T. Cont is a special case of cont T. Parsec from like the various parsing packages, this is like a special case of parsec T. So this is a very common pattern you're going to see in the wild. But not all monads are special cases of transformers. For example, the maybe monad is not a special case of maybe T identity. In fact, that would be a bit difficult because maybe T is defined in terms of maybe, so you'd have like a loop there, which would be problematic. You could define separate types, but whatever. For the same reason, also for ergonomic reasons, like it's also just easier for the maybe type to not be defined that way. It's just easier to use if it's not a monad transformer. So either is also not defined as except T identity. The list monad is not defined as list T identity. In fact, for the IO monad, there's no such thing as like IoT. There is no IO monad transformer. Same thing for STM. There's no such thing as STMT. And for the identity monad, it's not defined as identity T identity because that would again be defining it in terms of itself, which would be silly. All right, so any other questions before I move on to the next section? Let's see.
I can forward some of the questions to you. Maybe
okay, go ahead.
So the first question is, if I stack multiple monads, is it necessary to invoke lift multiple times?
Yes. In fact, we're about to get to that in the next section of the talk. But yes, if you stack multiple monads, then you have to call lift to dig down one layer at a time to get to like the actual effect that you want to run, which can be tedious and problematic in some ways. So, but we're going to talk in just a second about how the MTL package addresses that issue.
The next question is about readers. So maybe it's useful to go back to the definition of reader T
yes.
in the slides.
Yeah, give me a second to find it. Yeah. Oh, sorry.
So we can see here that reader is defined as R to MA inside the definition. We also do M and then R to A inside the monad.
Sorry, I didn't understand the question.
Right. So the question is that
sorry. I see the question now. So basically, it's saying why is this here not inside the monad? So why is it not M wrapping a function from R to A? And so the answer is that so you wouldn't be able to implement the various type classes for the reader T monad transformer. So correct me if I might be wrong, but if I remember correctly, if you try to implement a monad instance for that rearranged type, it's not going to work out. So that's why it has to be like this shape here.
Another question is, are there any use cases of lazy and strict writer T, or should you just always use the CPS version?
So there are use cases for, so to answer the question, there is a use case for lazy writer T, but it only works with certain base monads. That's the simple answer I can give. So like if you set things up so that like you preserve laziness all the way through your stack, then you can in some cases like actually produce a lazy result and it all works out. But for many common base monads like IO, for example, lazy writer T is just not going to work. It's just going to keep like buffering up. It's going to be very inefficient at what it does. And it's often easier to simulate writer T as state T under the hood. And there's actually, I think one of the modules in the transformers package actually does this. So like there are various flavors of writer T, and one of them is just implemented as state T under the hood, which allows it to be more efficient with respect to strictness.
Thank you.
Yeah.
The next question is about except T. So that's one of the ways to do errors in Haskell. I think there's many different ways. So what is your view on except T, E, and then IO? Should this?
Yes. So I'm going to talk about this on a later slide in the misconception section. But the short answer is that I usually don't layer except T on top of IO. I often use it in pure monad transformer stacks that don't have IO as a base monad. But my personal preference is to just use IO for exceptions and not except T. To make an analogy to like other terms, like this is like the common like checked exceptions versus unchecked exceptions debate in other programming languages. So except T is kind of like checked exceptions, kind of, and IO, just using IO without except T is kind of like unchecked exceptions. But there's some, the problem though is that like you can never really completely get rid of IO. So if you like layer except T on top of IO, you get kind of the worst of both worlds. You get checked exceptions and unchecked exceptions. And there is like a package called unexceptional IO, which tries to like define an IO type where you just get rid of all the unchecked exceptions. But I find in practice, it's just easier to just use IO. There's another reason I slightly prefer to use just IO, which is that IO, the exception handling for the IO monad is more efficient than exception handling using except T. So if you're performance sensitive, then I would also recommend just using IO for exception handling.
Thank you. I'm going to group some questions together. So we spoke about a couple of transformers. And so we talked about how most monads can just be special cases of their transformers using identity. So is there a reason that there is no IoT and SMT, for example, they just can't exist? Or is this because of performance reasons that we're skipping the identity here?
So the simple answer is they cannot exist. Let me give you an example why you, like for STM, there's a very good reason. Well, first off, I don't think you could even implement it. But even if you could somehow implement STMT, that would be undesirable because then you could make the base monad IO. And then you can run arbitrary IO actions inside of an STM monad, which is exactly what STM was designed to prevent. So STM is specifically only permits a certain set of actions so that it can roll things back. And if you permit arbitrary IO, then that's no longer safe. But so for IO, so the short answer is you can't define an IoT. It's just not possible. So there actually is something which is, I would say, is like morally, the closest thing morally to IoT would be the free monad transformer, which I'm not going to talk about, but it's like that is the magic keyword for like if you want something like IoT, that is like the closest thing in the Haskell ecosystem to that. Yeah. But IO itself, you cannot create a monad transformer analog of it.
Let's do one more question. So if you have a plain definition of a monad like state or list or reader, is there a way to sort of mechanically derive the transformer from that using sort of prescriptive steps?
No, there is not like an automatic way to take a monad and generate an equivalent monad transformer. A lot of it is just like intuition, just kind of be like, I think the M goes here and just seeing if that works out or not. That's basically the way a lot of these transformers work.
Great. Thank you for answering questions. Let's continue with the talk.
All right. So the next part of the talk, I'll explain. I'll talk about the transformers and MTL packages. So far, everything I've talked about is from the transformers package. So the transformers package provides concrete monad transformers like state T. It also provides their simple analogs like state. And so it's not just a monad transformers package, it's also the monads package too, because a lot of common monads are, that's their canonical home. It's like the state monad, that is its canonical home, is the transformers package. It also provides useful utilities for each transformer. So like the put function for the state monad transformer. And it also provides the monad trans class, which provides the lift method. So then you might wonder, okay, if all those things are in the transformers package, what is this other MTL package? Why do we use it? What is it for? And which of these two packages is the real monad transformers package? And so this section is going to explain that. And the way I'm going to, but just to explain it, I first need to explain, I need to motivate the MTL package and why it exists and what it does. So the problem with the MTL that motivated the MTL is the one that one of the questionnaires just asked, which is that like, if I stack multiple transformers, do I have to keep like calling lift? And the answer is yes. Here's an example of doing that. So here we have some computation which combines, well, nests two effects on top of IO. So we add except t, and I just got through saying like I don't like nesting except t on top of IO. This is a very contrived example, but let's just go with it for right now. So I want to nest again. So actually, you don't want to nest state t on top of IO either, for reasons I'm not going to get into. But so anyway, so we're going to nest the two effects, except t and state t on top of IO. So now if I want to like access an IO action, I have to call lift twice. The first lift skips past the state t. The second lift skips past this except t, and then we can do something like printing. So that's what this is doing here. And if I want to dig one layer deep to access an action from except t, I have to do throw e. So I have to do lift to call throw e. And then, but any action that's at the top level, like state, I don't have to lift it. I can just say get, and that works because that's the outermost monad transformer. So the MTL package tries to solve this problem by auto-lifting functions for us. So for example, there's this monad IO class from MTL, which basically provides this lift IO utility. And what it's designed to basically say like, okay, I just want to embed an IO action. I just want to keep calling lift until I get to the IO, presuming there is a base, presuming our base monad is IO at the bottom of the stack. I just want to keep lifting until I get there. So obviously there's a monad IO instance for IO. So that's just the identity function because we're there. So we don't have to do anything to lift IO actions into IO. But for each of these other monad IO instances, it basically says, okay, for reader T, if the base monad supports monad IO, then so does reader T. And the way it does it, it just uses lift to delegate it to the base monad. And that's how every other, like you could literally implement the exact same monad IO instance for every single monad transformer. And the only one that's different is the one for IO. They just keep digging in using lift. And so if we have that instance, then we can just say lift IO and it does the right thing and it just calls print in the base monad, the base IO monad. If the monad at the bottom of the stack is not IO, then it'll be a type error because the instances won't resolve. We can also do the same thing for the state monad. So like this is a monad which provides two methods, get and put. And so remember that this is from the MTL package. So because we actually already introduced a get and put method from the transformers package. And these two methods are similar in spirit, but like they're canonically different modules. And for the monad state, for the special case of the state monad, the state monad transformer, the two gets and the two puts are the same. So the get method is the same as the get from the transformers package if we are in the state monad. And same thing, like the put method from the MTL package is the same as the put function from the transformers package if we are in the state monad. But for every other monad, these get and put methods will take care of lifting until we get to a state monad, and then they will use that. So that's the main difference. So both packages provide a get and put method, but the get and put from the MTL package are more general. They'll work as long as there's a state monad somewhere in the stack below us. And just like the monad IO instances, it's just trivially using lift to lift things over and over again until we dig down to the right state monad. So you could just like automatically derive these instances. In fact, I believe if I remember correctly, Alexis King had a blog post where she advocated that the default, at least for some MTL classes like these, the default implementation of these methods should just be like these auto-lifted instances. So you wouldn't have to like write them out every time. And I don't know why we don't do that yet, or maybe it has been done. I haven't checked, but yeah, so anyway, these are very mechanical instances to write. Okay, so So even if we're armed with that instances, that doesn't change our code because we're already in the state monad, so we don't have to lift anything. So it's still just get. The only difference is like maybe now this get is coming from the MTL package instead of from the transformers package. And the last MTL class we're going to cover is the monad error class, which provides a throw error function and a catch error function. And again, for like the special case of except T, then the throw error and catch error from MTL are synonymous for throw E and catch E from the transformers package. But the other instances now get a little bit more tricky. So for throw error, we can trivially lift those instances. It's just like lift, lift, lift. But for catch error, it's not mechanical anymore. So for each monad transformer that supports monad error, the way you lift the instances is you have a special function for lifting it for each monad transformer. So there's not just like an automatic way to derive monad error instance for every single monad transformer. Moreover, there are some monad transformers that just cannot implement monad error. It's like there's just not a way, mainly because there's just not a way to implement catch error. In fact, like there's actually another package called the exceptions package, which provides a slightly different class similar to monad error. It's called, so it splits monad error into two classes, monad throw and monad catch. So monad throw only supports basically throw error, whereas monad catch supports throw error and catch error. And so that because like the reason why is because like for monad throw, you can basically implement that for any monad transformer. Whereas for monad catch, you want to separate it because you cannot implement that for every monad transformer. In fact, for like most use cases, I would recommend using the exceptions package over the monad error class from the transformers package. And so, okay, so now that we have this monad error instance, that does simplify our code a lot. So now we can just say throw error instead of lift throw error. So there's not really a good way so we got rid of the lift for throw error and there was no lift for get. But is there any way we can get rid of this lift IO? And unfortunately, there's not a good way to do that unless you like take all of the IO utilities in the Haskell ecosystem and wrap them in lift IO. I mean, even then you couldn't actually do that. But for many utilities, you'd have to pre-wrap them in lift IO to not incur this overhead here. There is a package that tries to do that for as many utilities from base as possible and some other packages too, which is called the unlift IO package. So if you're just kind of looking for a package that just wraps a whole bunch of stuff in monad IO, then this is the package for you. All right, so what about the maybe T class, right? That was our very starting example, but like, is there like a monad maybe class? And the answer to that is there already is such a class, and it's called alternative and monad plus. Actually, these are used for more than just like a monad maybe class, but spiritually, these are the monad maybe classes. So empty is how you fail with a nothing, and alternative operator is how you fall back is basically like how you catch a maybe error. So if the first computation fails, then you can fall back to the next computation. Okay, so now with that context, now I can explain what the MTL is and how it relates to the transformers package. So the MTL is just an extension to the transformers package. So it's not like a replacement or substitute or competing package. It's basically transformers plus some other stuff. And the MTL package re-exports most of the transformers package. They both use the same types. So like the types in the MTL package are simply re-exported from the transformers package. And pedantically, both of these packages are the monad transformers package. And often in discussions about effect systems, I prefer to refer to these packages by name. And the reason why is because these packages have different trade-offs. They tend to be used idiomatically in different ways. And those trade-offs inform discussions about effect systems and their pros and cons. And so yeah, the big difference between the two packages is that the MTL package uses type classes like monad reader instead of like being hard-coded to specific monad transformers. Another tiny difference is that the module names in the MTL are shorter. So like control.monad.state instead of control.monad.trans.state. Even that is still like way too long for me. Like I think this could have just been like MTL.state. Like I don't know why people have to come up with such long names. So here's the difference idiomatically between the two packages. What you're often going to find is that the transformers package tends to be used in very short and localized ways. So like our original read3ins example, we just dipped into it briefly inside of this read3ins functions, and we then dipped out using runBBT. So from the outside perspective, it's as if we hadn't used it at all. It's just an implementation detail. It doesn't show up in the types. Whereas the MTL package tends to be used more in like a long-lived and global way. So like a lot of applications will define some sort of a God monad, like an app monad, for example, that has all the effects they're interested in. Like in this case, reader T, config, maybe TIO, just some contrived example. And then they'll say, okay, deriving, and then a whole bunch of instances. So functor, applicative monad, alternative monad plus, and then most notably, like monad IO from the MTL package and monad reader also from the MTL package. Okay, I'm gonna pause for questions to see if, yeah.
We have a couple of questions, yeah. So one question is it useful to use a monotransformer multiple times? So for example, you could do state t int and then state t bool inside of that, and maybe even multiple copies of state. Is there any use for that?
I would say, in theory, yes. In practice, no. What you often find is that, like, if you want to nest multiple state transformers, you just combine them into a single state transformer. I think, like, actually the better way to do this, if you want to combine, like, if you want to have like an application with multiple substates, it's I feel it's easier to just use to have a single unified state and then use something like the lens package to access and modify the state of interest. Because the lens package actually has some nice utilities for working with the MTL package. So you can basically say, like, I'm going to zoom in onto the substate of interest and then tweak that a little bit. So I think like that tends to be what you want to be used. But so also nesting state monad transformers does not work well with the MTL, because the MTL utilities can only dig down to the outermost state monad transformer. It does work with the transformers package. The transformers package works just fine because you're very explicit about how many times you lift. And you could, like, for example, you could define like useful synonyms that lift to the desired state level. But in my opinion, it's not worth it.
Thank you. Another question. So there is also a monads DF package, and it's kind of like similar, but rather than using functional dependencies for defining the classes, it uses type families. Is there a technical reason that MTL is so much more popular than using type families, or is it just because of historical reasons?
So I don't know. I have not used the monads TF package that much personally. If I had to guess, the way I would evaluate the relative merits of those two packages is by trying to study how good the type inference is for like various utilities written in those packages. But yeah, I don't have any strong opinions about like multi-parameter type classes versus type families.
Thanks. Another question, maybe a bit of a can of worms, but what's the difference between monad plus and alternative?
Oh, yes. So yeah, these two type classes are almost the exact same. Well, they are the exact same class. So I mean, from my point of view, these are the same class. Like, so some people have like, some people have like opinions on like what laws these two classes should satisfy. In my opinion, the only laws these two classes should satisfy are the monad laws. Like from my perspective, these are basically just higher kinded monad classes. So as long as they satisfy like the identity monad law and the associativity law, then you're good. Some people will like add additional laws on top of that, but I don't give that much credence myself. But yeah, I think of these as the same class. And personally, I think like alternative is the only class we actually need.
Thanks. One more question. So if someone is writing a library and they want to provide a transformer to use for users for their library, which package should they use, or should they provide their monotransformer in many different packages?
I would say like MTL seems to be like the consensus of the Haskell community. So like if you can define your monad transformer, and if there's like some equivalent class for working with your monad, that's probably what you should provide. And there are other effects packages, but I feel like none of them is close to dethroning the MTL as like the Haskell community consensus package.
Thanks. Those are all the questions for now.
Okay. So now I'll address like a few common misconceptions that come up in the context of monad transformers. The first one is this, you'll see like more in talks about like, you'll see this often from like people plugging a new effect system, is like the concept that monad transformers, especially like MTL, are slow. And this in particular was promoted by Alexis King in her talk, Effects by Less. Oh, sorry, she did not actually make this claim. I want to be clear. She made a much more nuanced claim, but I feel like a lot of people misunderstood the actual claim that she made, which is that, so MTL does have the highest performance ceiling out of all the effect systems, but only if you mark code as inlineable. But there's a huge downside to marking all your code as inlineable, which is that you can get significantly slower compile times because you have to do whole program optimization at each use site. But it's not correct to say like without qualification that transformers are slow, because like actually if you're willing to pay that compile time cost, then the MTL is the fastest of the effect systems, as far as I know. So another misconception, well, not really misconception, but like, again, you should be like very precise when you say something like this, is that some people say like never use, except T or state T or writer T. And that advice I would say is correct if your base monad is IO. In fact, like there's some great blog posts, I think by Michael Stoneman, where at least he explained why for except T and state T, why there's a bad. And writer T is just like bad with IO because of like strictness issues. And yeah, so if your base monad is IO, then you should definitely steer clear of these three monad transformers. Just use IO, basically, like that's what you should be using. But those transformers are still useful if you have other base monads. Like we actually saw an example of this earlier in the talk with the parser type. So we had state T layered on top of this list base monad, which is totally fine. That's a very useful thing to do. I mean, this is not a good parser type for other reasons, but it's not because we use state T in our monad transformer stack. And so another viewpoint is like the only only effects we need are like reader, writer, state, and accept. And so sometimes you see like people who are promoting algebraic effects try to say like, okay, like we only support these effects, but that's all you really need. And I kind of take issue with that. So like I feel like there's several other monad transformers which I consider like really important and fundamental support, but many effect systems don't support them. They fail pretty hard on them. One is like list T done right. Note that this is not the list T from the transformers package. So the transformers package has the wrong broken list T in it, but there are several packages on Hackage that have a correct implementation of list T. And so yeah, but that I consider to be like a very fundamental monad transformer. And I use it a lot in my own code too. Another one I consider really fundamental is the free monad transformer. Again, not going to go into that, but I consider it to be like a really important monad transformer that should be in a lot of Haskell programmers' toolbox. And then finally, like there's the continuation monad transformer. I don't use this one as much myself, but like it is also another monad transformer that a lot of these effect systems feel hard on. And just because it's inconvenient for them to model using their framework. Whereas the transformers package and the MTL package handle these just fine. Like they have no issues modeling these. So the key takeaways I want you to get from this talk is that the monad transformers are probably like the most natural effect system. So like they are just automating what you would have otherwise written by hand and just making it more nice and ergonomic to work with. They're not trying to do anything like super clever. And monad transformers are composable. So each of the standard transformers does one thing and does it well, and you can stack them to unlock new effects. In fact, like most interesting monads are just the composition of like one of these few standard transformers. And finally, the monad transformers, specifically MTL and the transformers package, they're mainstream and widespread for good reason. And I feel like they should be like the default choice for most new projects, unless you have like a really compelling reason otherwise. And so if you like my work and presentations, you can follow my work in progress on my various social media accounts at this Linktree link here. And also, quickly before I conclude, I would like to take this moment to briefly plug trans rights in the US. I know most of this audience, at least right now, is European, but if anybody watching this either live or remotely is located in the US, I implore you, I just want to let you know that gender-affirming healthcare is currently under attack in the US. And many trans people, like myself, rely on stable access to hormone replacement therapy, and legislators are actively fighting to take that away from us. And so even if you're not trans, I'm addressing you. Please help defend us trans people from this ongoing political assault. And in particular, if you are located in the US, you can help take direct action by visiting transequality.org/action centers. And with that, I'll conclude my talk.
Thank you, and thanks for including that message as well. We have currently one clarification/question about the remark around performance. So there was this kind of like a remark that this code needs to be marked inlineable, and the question is if does this apply to user code as well, or is it only library code that needs to be inlined, or only code within the transformers package itself?
It's user code that has to be marked inlineable for this to work.
Yeah, so yeah, thank you. Then maybe one more question, but feel free to ignore it if it's too long.
Oh, yeah, no, I can answer this. Yeah, so the question here is, what is the wrong implementation of list T? Let me just quickly, if you share my screen really quickly, I'm just gonna like show that. So in the transformers package, there's control.monad. Oh, they finally got rid of it and deprecated it. Oh, that's amazing. Okay, so let me actually go back to an older version. But there used to be, let's see. Yeah, here you go, control.monad.trans.list, which was the wrong broken. This is not the way, so like you think like, so this goes back to the original question, which is there a way to mechanically take a monad and promote it to a monad transformer? And I said, okay, a lot of it is just like figuring out where do I insert the M? And so this implementation did the wrong thing. And so you think, okay, maybe I just put the M around the list. That's not how you do it. Okay, so all of the correct implementations are basically equivalent to this education. So I have this educational implementation called list.transformer, which shows the simplest correct way to do it, which is, sorry. So basically you have to define a type. Basically you have to insert an M between each element of the list. So in other words, you have to run.
Increase the font size. Just
oh yeah, sorry, let me just, there we go. Yeah. So the way it works is that you have to insert the M base monad in between each element of the list for it to do the right thing. So in other words, you have to like run the action to get the next element, which will either be like, you know, an element of the list or the empty list. And if it's element, then you just go back and you just keep like running M to get the next action. So that is the correct way to do it. And most of the other implementations of list T done right are isomorphic or equivalent to what I just showed you here. So that's how you know which one's the correct way of doing it. And it's not just like theoretically more correct, it's also practically better too, because this way of implementing list T ensures that the values actually stream. So you don't have to buffer them all before getting the result. So you can actually like get the values as they're being produced and do something with them instead of just like holding on to them in memory, which is nice.
Thank you. In the meanwhile, we have two more follow-up questions, so I can just forward them to you. So the first question is, like, wouldn't you say that maybe monotransformers for effects feel natural just because they're so used so often in Haskell? So it's kind of like a chicken and egg problem.
No, I think if reading the question, that's not exactly what they said. They say because the monads, so basically like because Haskell is like Haskell programmers have like monad brain, they tend to think of effect systems through the lens of, you know, monad transformers. Whereas like if you had a language that was not so monad centric, like maybe it was built from the ground up to be like, you know, to be like, example would be like Unison. Like Unison has its own like, it's built from the ground up to be like centered around like its own effect system. And so like maybe if we did that, then we wouldn't reach for monad transformers so much. I would say like, again, for the simple effects like state, reader, writer, yes. But for the more complex effects, I feel like monads, again, like list T, free T, cont T. I feel like monads and consequently monad transformers are like the right abstraction level for those effects.
There is another question about the n times n problem with MTL, which I'm not sure if we have time to explain, but I think it would be good to have your opinion on it as well.
I can actually quickly cover it. So like I can just quickly explain it by going to this slide right here. So you notice that like for every monad transformer we define, we're basically imposing a tax on the entire rest of the Haskell ecosystem. Because we're saying like, okay, now if I define this monad error class, now every single monad in every monad transformer in the ecosystem has to implement monad error. And that leads to like a quadratic code blow-up. I would say like in my opinion, it's not an actual n squared problem because like because again, we don't need to define a class for every single monad. We only need to define classes for the standard ones. Okay, so like yeah, there are quite a few standard ones, but there's like, in my opinion, a mostly finite set of them. Because again, like state, reader, writer, free monad transformer, cont T. You could argue that monad plus is also like the monad list monad transformer too. So it's like monad plus and alternative are like monad maybe monad list. And those like the combination of those effects basically handles everything, right? So like, yes, you might have like some application specific monad, like monad DB or whatever, but you're not going to ask like the whole ecosystem to implement monad DB. Like nobody's going to implement your proprietary monad class. So if you're just focusing on like what are the standard monad classes that everybody needs to implement, like there's actually not that many of them when you actually dig into it. So it's really more like not an n squared problem, but more like an m by n problem where m is like a finite small number that doesn't scale with n.
Thanks. Maybe you have time for one more question. So the question is, do you recommend defining your own transformer if you're using application, or should libraries be doing this?
It depends on what you mean by defining your own transformer, but like what you'll find for at least application code is, is what I showed you earlier with like the app monad, where you just like define your own monad, not a transformer, which internally is implemented as like some monad transformer stack. And then you just derive all the instances you're interested in. For library code, I would say, I think it's fine to define so let's say you might want to provide your own, so like, let's use an example, like parsec, the parsec T type I think it's fine to define your own transformer. So like for parsing packages, they often define their own monad transformer and their own corresponding class, like monad parsec or whatever. Yeah, I think that's fine. It's just that like, I think for those composite transformers, there's no expectation for the rest of the ecosystem to like provide the lifted instances. It's just like you add it if you need it for your application, but like I think there should not be any expectation from the ecosystem to implement globally all of those instances.
Yeah, thanks a lot for the talk and for answering the questions. Even though you couldn't be here with us physically, I think it was very good.
Yeah, I hope to be here next year. Sorry I couldn't make it this year.
Thank you. Bye-bye.